the industry is looking for maximizing transparency. And today, the best solution to achieve nearly seamless facades in glass is to work with laminated glass. Of course, as the glass pane dimensions increase, so do the joints, and that is quite of a problem. And not everyone is blessed with a nice climate when you can limit yourself to laminated glass. Sometimes you need to work with IG units. And so we've seen recently some efforts from the insulating glass units manufacturers to propose new concepts where the two verticals have been replaced with transparent solutions. So here you can see two examples. And the spacer that is being used is typically a rigid material like glass, polycarbonate, or PMMA. So these materials will achieve a hardness that is quite high, between 80 and 100 on the D scale. And that guarantees the dimensional stability that is needed for the IG units. Now, the hardness and rigidity also means some limitations in terms of production. So, difficulty of cutting, fragility as well. Difficulty to bond. So, typically double-sided adhesive tapes are being used, which are transparent. Now, as you try to use a tape on a rigid material, you will very easily have air entrapment that will lead to bubbles that will impair the aesthetic appearance of the final result. Plus, those tapes are not ideal solutions and don't really like the stresses that are induced by a rigid spacer. So, on the other hand, the two horizontals, they are kept in a traditional build-up because in order to ensure the long-term durability, of course, we need to include a PIB, we need to include desiccant. So recently, we developed a new two-part condensation cure system, which enables bulk cure in a few hours. This formulation does not have a filler in it, and this results in crystal clear solution, as you can see on this slide and also on our booth. The absence of the filler means that we will have some different properties from a mechanical point of view in terms of tear resistance. The filler will also help you to improve, in some cases, adhesion. And the filler will also help you to achieve certain tensile strength. So if you work without a filler, you are also reducing the capacity to extrude the silicone in a vertical joint. So gun-grade applied silicones, like we are used to for a vertical joint, it's not possible with this technology. We can play around with the formulation. We can achieve a variety of hardness that goes from very soft gels to soft elastomers. But what is really, really unique about this technology is that it is able to develop post-cure adhesion on substrates. So if you take a piece of conventional structural silicone, like our 993, for example, you make it cure on Teflon, you take it off, you will never, after cure, make it stick again to any kind of substrate. So this technology can do that, and in a quite easy way. So we have here a fully cured product that is transparent and that has the unique capacity to be bonded after cure on the substrate. And it is quite robust in adhesion, even if there is no filler. We have performed adhesion tests and verified that we can develop post-cure adhesion to metals, copper, aluminum, different types of finish, all kinds of plastics, and of course glass, stainless steel, and so on. And the trick is actually to use a primer. So when you apply the primer on the substrate, you put both in contact and you wait some time, you will develop cohesive failure, as is the case when you directly dispense the silicone and let it cure on the substrate. So this is another way of just the previous explanation. So we need to prime the substrate and not the silicone spacer. The primer time is about a few minutes. Typically less than 5. It will vary a little bit depending on the condensation, the temperature and the humidity conditions. You then put both elements in contact, and you wait a certain contact time, again, from 3 to 10 minutes, depending on conditions. If you prime the spacer, you will not develop adhesion. And if you assemble the unit before having waited enough time, you will not develop adhesion either. But other than that, that's it. So there's no difficulty about the spacers that we can see. Performance-wise, it's a flexible material. Actually, I forgot, I have a sample here. I can show you. It's totally flexible. We achieve a hardness of 50 on the 0.0 scale. We reach a Young modulus of 25,000 Pascal. So really the dog bone test piece, the real material property. And in H pieces, our tensile strength is set at 40,000 Pascal. So this is really based on extensive testing. So we have performed ETAC testing, as you know, varied aging conditions, and verified that our properties are stable. Now, as we are working with an unfilled system, we see some variety, not due to the aging, but due more to the manufacturing of the H pieces. And so we have set at 40,000 Pascal our tensile strength limit. So this means we can take 40 kilogram of load per linear meter when you have a bond of 10 millimeter. For the moment, that is our typical size. The elongation at break is 85 to 90%. And the specific gravity is less than 1. As we don't have a filler, we also have a much better thermal conductivity. So, as you know, filled silicones are stated at a lambda value of 0.35 watt per meter Kelvin per ISO 10456. So here we are at 0.16 watt per meter Kelvin. We also verified the moisture vapor transmission rate. So this one is at 31 grams per square meter and 24 hours. In terms of aesthetics, we're talking about crystal clear. Here you can see the light transmission measured according to the ASTM D1003. You see that we are around 90%, depending on the wavelength that you take into account. And the haze is also excellent, less than around 3%. This is still 100% silicone technology, so it comes with all the durability and also the non-yellowing aspects that you can anticipate for this system. The original idea was to use this material for this kind of application. So if you remember, when we were kids, we could easily grab stuff out of supermarket shelves, but with energy efficiency requirements, I have now in my supermarket those monolithic doors, and the more upscale supermarkets even have IG units. But of course, IG units with a big, thick black line that prevents the visibility of the merchandise behind. So there are quite some efforts to eliminate this. And here we are dealing, of course, with an easy case. Durability that is needed for this kind of IG unit is not the same as in a building. It's much more probable that an old lady will smash the glass with her cart than that there will be condensation. So it's an easy system that we have. We have just a spacer that is directly acting as both spacer and secondary seal. It's bonded post-cure with the primer step to the glass panes. But we thought that this technology is really promising and has some potential as well for architectural IG unit applications. So we've been playing around in the lab since quite some time now, evaluating different concepts. So here you can see this is the fridge setup with just the dose spacer. We realize, of course, that this one is not going to be very durable. It's acting as a reference. There is no primary seal. You can see here that we are assembling 4 pieces of the spacer together with just a conventional black silicone gun grade, what we had in the lab. You could easily assemble it with different transparent solutions or have it cast in the right shape directly. You can see as well that for the moment we have an original way of integrating the desiccant. So it's a bag, plastic bag, with the amount of desiccant that we need. This is R&D, right? The next system, we have misaligned the dust spacer with the edge of the glass. So you see it's a little bit out of it, and we stick on the edge a metallized foil. just to enhance protection of the spacer and to see if this metallized foil is going to improve the durability. As we know that silicones have some moisture vapor transmission. It's not the primary seal, right? So we want to understand that. And then in the third step, and that's really our concept today, what we do is we inverse the order of the secondary seal and the primary seal. So the butyl is applied on the edges of the glass. The DOW spacer is just protruding 1 millimeter, and so everything is aligned. And then you have the metallized foil on top of it. This foil is sticking to the spacer with the primer, and the butyl is also sticking to it. When you look at it, in the face, you see a very clean edge with just a tiny black line. So that's our concept, and we have now performed internally a static, what I call a static climatic test. So it's basically put it in the oven at different conditions of temperature and humidity. So we have here on the left 23 degree and 50% humidity, and 50 and 80 on the right. This blue curve is actually a simple bag of desiccant put in the oven as a reference. What we evaluate is the weight increase, and when we stabilize that weight increase, we assume that this desiccant has reached its maximum capacity. And so if your unit has increased by that weight amount, we will not have a desiccant that is functioning anymore. So we can see that the two concepts, the one from the fridge and the one with the aluminum foil, reach full capacity of the desiccant after 350 days. This one is the one with the butyl, is still performing for the moment at those conditions. When we look at higher temperature and humidity, all the diffusion process is accelerated, of course, and so we see that the full capacity is reached after less than 100 days, but still performing for our concept. So based on that, we are extrapolating a bit what the lifetime expectancy could be, but of course, this is not the official 1279 test. This is not a cycle test, so this is what's next. So we have prepared new units. You can see that we have improved a bit the aesthetics of assembling of the 4 pieces of spacer together. You still see the back, but if we were doing everything, there would be no challenge left for the industry, right? And so the goal is now to put this in a 1279 test and see how it behaves. But as you know, this test requires about 15 units, and so this is still going on. So this is the status today. This material is not yet viable off the shelf, but we are working on it. We are setting up the whole chain. And we are really opening up for discussion with the industry, collaboration with the industry, to develop some nice concept together where you can exploit this performance that I have showed you today, and maybe as well exploit this transparency working with the lighting transmission capacity that this has. So thank you for your attention, and feel free to ask questions.